A brief synopsis of R, presented by Instructor Anthony. So, without further ado, let us begin. What is R? R is a statistical programming language that excels in hypothesis testing, regression, classification, clustering, and more. That's fancy language for saying we transcribe observations and we want to classify the properties of our data sets. Not to mention data visualization and handling. We want to create illustrations of our data sets and try to communicate our findings to non-technical audiences. Additionally, there are built-in functions and add-ins that you can add for different specialties. Depending on what you would like to use R for, you can use it for statistics and developing advanced models, or you can use it for data cleaning, aggregation, and summarizing. The best part about R is it's open source and anyone can download it at its CRAN website. It can be used for Windows or other devices, such as Mac. RStudio is an integrated development environment, or also known as IDE, and is used to create and visualize R code. The idea is we want to read and run our code through a development environment. And this means that we want to understand the syntax of R, and we want to use it to make the code reproducible so that other people can also use it. And we can download the integrated development environment, RStudio, to read our source code. Now, I primarily use R for summarizing and analyzing datasets, including CSV files, which are exported from Microsoft Excel. Some data frames, which are variables that are stored locally within R's environment, can be read and analyzed from the source code itself. Libraries. The first step is to glimpse at a data frame. A data frame is just a type of variable that we will store CSV files. So one example is the iris. The iris is a data set consisting of sepal length, width, petal length, and width, and species. So there are 5 columns in this data set and multiple observations. Each observation is recorded in a row. For instance, the first row is a measurement whose sepal length is 5.1, whose sepal width is 3.5, whose petal length is 1.4, and whose petal width is 0.2. The species is Setosa. Now, we can observe that a feature of the data set is represented by a column. So there are 5 features of the data set in this data frame. Some of the features are numerical data types and the others are characters. The species is a character data type because it's in a text-based prompt. And it's actually categorical because there are multiple records with the same species instance, which is Setosa, but there are also other species. The other columns are numerical types. So those are represented by numbers. And there are 2 types, numerical types of data. There's an integer and there's a double. If a column is numerical, we can apply descriptive statistics to better understand where the center is, which can be obtained by taking the average or the median. The average is we add up all the values and we divide by the number of values, and the median is we order it from least to greatest and take the middle. Or we could also observe how the data deviates from the center. The second order moment is the variance, and if we take the square root of the variance, we obtain the deviation. There are other measures of spread, including interquartile range and range, which is the max minus the min, but variance and deviation is very often used. So suppose a column or categorical factor that is a character column with high multiplicity, so it appears multiple times, If we have such a column, we can aggregate the data and summarize by that group. So species is a categorical variable, and we can group the data with similar observations and apply a formula to the other columns. If it's numerical columns, then we can apply the average, the max, the min, or the median, things like this. So the next thing we're going to do is we're going to aggregate and group the data. So we observe that the species is a categorical variable. We can group the observations by that categorical variable, and we can apply descriptive statistical methods, including taking the average, which is observed in the statistics.mean column, taking the standard deviation, which is the square root of variance, in the statistics.sd column, and we apply this for each species. So, and we do this for every numerical type of variable. Petal length for each of the species, Setosa, versicolor, virginica, and petal width, sepal length, and sepal width. Because there are 3 species and 4 numerical columns, there are 12 total rows in this aggregated data frame. There are also other descriptive statistical measures such as the interquartile range, the skewness, and the median. The skewness just determines how the data is distributed from the center. Is most of the data to the right of the median, or is it to the left? If the skewness is equal to the 0, the median and mean are equal. So here we can see that the average petal length for the different species is different. Definitely for Setosa, it has a significant less mean than the versicolor. So it's about 3 times less. Now, we want to actually visualize this data instead of looking at it at a table. So we can do this by creating animations or static visualizations. Let's create animations of data in R. To the left, we have a scatter plot, and we have a transition between the species. We have a density plot, and to the right is the petal length as special species type varies. Thanks for watching, and remember to like, comment, subscribe to my YouTube channel.